December 25, 2025, while much of the world was focused elsewhere, a quiet but significant event unfolded in the skies over China. A third prototype of China's emerging sixth-generation fighter took to the air, just 1 year after its first public appearance. This was not simply another routine test flight. It was a signal of confidence, momentum, and an unusually fast development rhythm that immediately drew global attention. In modern military aviation, the number of prototypes matters. Flying a third distinct airframe in such a short time suggests that engineers are not just validating basic flight safety, but actively comparing different design solutions in parallel. This approach accelerates learning, reduces long-term uncertainty, and reveals how seriously a program is being pushed forward. Rather than focusing on combat claims or future conflicts, this third flight forces a more important question. What does this pace of experimentation reveal about how next-generation aircraft are now being designed and tested? The third flight highlights a deeper transformation in how advanced military aircraft are being developed. Traditionally, next-generation fighters followed a slow, sequential process. One prototype, years of testing, incremental refinements, and only then a revised design. What we are seeing here represents a clear departure from that model. Multiple prototypes are being flown within a single year, each exploring different aerodynamic layouts, propulsion solutions, and control concepts at the same time. This parallel experimentation allows engineers to collect real-world flight data much faster than computer simulations alone ever could. Instead of committing early to a single configuration, designers can test competing ideas simultaneously and converge on the most effective combination later. While this approach increases short-term cost and risk, it dramatically shortens development timelines and accelerates learning. More importantly, it reflects confidence in digital design tools, flight control software, and manufacturing capacity. Rapid prototyping is no longer an experiment. It is becoming a core philosophy shaping how sixth-generation aircraft programs move from concept to reality. One of the most striking features revealed through these test flights is the aircraft's tailless configuration. Removing traditional vertical stabilizers is not an aesthetic choice. It is a deliberate move to reduce radar reflections from every direction. Vertical tails are among the largest contributors to radar cross-section, especially when viewed from the side or rear. Eliminating them enables what engineers call all-aspect stealth, making the aircraft significantly harder to detect regardless of its orientation. However, tailless designs introduce serious challenges. Without vertical tails, stability and control must be handled almost entirely by advanced flight control software and engine thrust management. Small, continuous adjustments are made thousands of times per second to keep the aircraft stable across all flight regimes. This requires extremely reliable sensors, powerful onboard computing, and highly refined control laws. The successful flights suggest these systems are maturing rapidly. The design reflects a shift towards software-defined aerodynamics, where stealth and control are achieved as much through code as through physical structure. Perhaps the most unexpected element of this aircraft is its three-engine configuration, a rarity in modern fighter design. Traditional fighters rely on one or two engines to balance efficiency, weight, and complexity. Adding a third engine signals a different mission priority altogether. Rather than focusing on close-range dogfighting, this layout suggests long-range endurance, heavy electrical power generation, and sustained high-altitude performance. A third engine allows greater redundancy and provides excess power for advanced onboard systems such as large sensor arrays, electronic warfare suites, and high-bandwidth data links. It also supports prolonged operations without compromising speed or payload capacity. The dorsal engine placement further hints at design trade-offs between stealth, airflow management, and internal volume. This propulsion choice aligns with the aircraft's apparent role as more than a traditional fighter. It is optimized to function as a command platform and force multiplier, prioritizing energy, persistence, and systems integration over pure maneuverability. What truly defines this aircraft is not how it flies, but what it is designed to do. Rather than replacing traditional air superiority fighters, This platform appears optimized for long-range coordination and battlefield management. Analysts increasingly describe it as a quarterback aircraft, a node that controls, directs, and amplifies the power of other systems rather than engaging every threat directly. Its large internal volume suggests space for advanced sensors, secure communications, and battle management software capable of coordinating unmanned aircraft. Instead of entering heavily defended airspace itself, it would likely operate from standoff distances while directing loyal wingman drones to probe defenses, strike targets, or draw enemy fire. This approach shifts air combat away from one-on-one engagements toward networked warfare, where decision-making speed and information dominance matter more than turning radius. In this role, the aircraft becomes a force multiplier, returning a single platform into the command hub of an entire airborne system. What has unsettled defense analysts the most is not any single feature, but the pace at which development is happening. 3 distinct prototypes flying within roughly 12 months represents a break from traditional, cautious aerospace timelines. This tempo signals a willingness to accept technical risk in exchange for rapid learning, something rarely seen in modern, Western fighter programs. By testing multiple configurations simultaneously, engineers can compare real-world data instead of waiting years for incremental upgrades. That compresses decision cycles and accelerates maturity. In military aviation, time is not just money, it is strategic advantage. A platform that reaches operational relevance even a few years earlier can reshape planning, deterrence, and procurement decisions worldwide. Even if final deployment remains years away, the perception of momentum matters. It forces competitors to react, reconsider assumptions, and potentially rush their own programs. In that sense, speed itself becomes a strategic weapon, one that reshapes the balance long before the aircraft ever enters service. The timing and visibility of the third flight suggest it was more than a routine test. It was strategic signaling. Conducted on a highly symbolic date and allowed to be widely observed, the event sent a deliberate message to global defense communities. It demonstrated confidence, continuity, and intent, reinforcing the idea that development is progressing steadily rather than experimentally. Such signaling serves multiple purposes. It reassures domestic audiences about technological progress while simultaneously shaping foreign perceptions. Even without releasing official specifications, visible flight activity forces analysts and rival planners to reassess timelines, threat models, and resource allocation. Uncertainty itself becomes leverage. In modern military competition, perception can be as powerful as capability. By showing sustained progress without explanation, the program compels others to prepare for worst-case scenarios. That pressure can drive costly countermeasures, accelerate rival programs, or alter strategic planning. All outcomes that benefit the side controlling the narrative of momentum. The emergence of a platform like this points to a broader transformation in how future air combat may be structured. Rather than relying solely on individual, highly agile fighters, air forces appear to be moving toward network-centric systems, where one advanced aircraft coordinates sensors, weapons, and unmanned platforms across vast distances. In this model, survivability comes less from dogfighting ability and more from information dominance, range, and system integration. Such aircraft could reduce the need for large numbers of traditional fighters by acting as force multipliers, managing drones, queuing long-range missiles, and directing battlefield awareness from outside contested zones. This shift also affects training, procurement, and doctrine, placing greater emphasis on data fusion, AI-assisted decision-making, and joint operations across air, space, and cyber domains. Ultimately, this signals a future where air superiority is defined not by speed alone, but by who controls the battle space before the first shot is fired. This program highlights a clear shift in how next-generation aircraft are being conceived. Future designs are moving away from incremental upgrades and toward clean-sheet architectures built around adaptability from the start. Instead of optimizing for a single role, New platforms are designed as flexible systems capable of evolving through software, sensors, and modular payloads over decades of service. The emphasis is also shifting toward reduced physical signatures, internalized weapons, and airframes shaped primarily by stealth and efficiency, rather than traditional aerodynamic norms. Control surfaces may continue to disappear, replaced by advanced flight control software, thrust vectoring, and AI-assisted stability management. At the same time, aircraft are being sized to balance range, payload, and information processing capacity, rather than close-in maneuverability. Most importantly, these designs reflect a future where aircraft are no longer standalone weapons, but central nodes in a wider combat network, built to manage information, coordinate assets, and adapt faster than the threats they face. The third flight represents more than technical progress. It marks a turning point in the pace and philosophy of military aviation development. What stands out is not just the aircraft itself, but the confidence behind it. Rapid iteration, visible testing, and a willingness to challenge long-established development timelines. That alone forces a recalibration across the global defense landscape. This moment underscores a broader reality. Air dominance in the coming decades will depend on who can innovate faster, integrate systems more effectively, and adapt designs over time rather than who simply fields the most advanced single platform. Prototypes flying today are shaping doctrines, budgets, and alliances years before they ever enter service. Whether or not this aircraft becomes operational on the earliest timelines, its continued presence in the skies has already achieved something significant. It has changed assumptions. And in strategic competition, changing assumptions is often the first step toward changing outcomes.